So probability density. Psi squared is the probability density. Psi is one of the wave functions in Schrodinger's equation. The probability density is the probability of finding an electron at a given point in space. So psi squared is the probability divided by the unit volume. The s orbital is spherical, so that's kind of nice. S and spherical, right? Spherical starts with S. So what we observe here is that the probability density decreases as the distance from the nucleus increases. And so we can make a plot of this. There's not a beautiful solution for this, but you can make a plot of this that resembles a multiple exposure photograph, or kind of like that picture I drew of Andrew. Of like, okay, let's look now. Where is he? Wait 5 minutes. Where is he now? So we've got this plot, and it's got a lot of dots. And so it's like you took an exposure every 10 seconds or something, and here's the electron, there's a dot. Here's the electron, here's a dot. What it's important to understand is that the electron is not moving around the nucleus like a moth around a flame. So up until this point, I've said, well, the electrons are doing something. They're, out there. They are actually doing something a lot more organized than a moth does. They're not just flitting about randomly. A moth is a Newtonian object. It is deterministic, and you can predict where it is and what it's going to do. It might be, it's really irregular, like a bat, flying around, but it can be predicted. An electron cannot be predicted like that. So in a sense, the electron's location is spread out over the entire volume of the orbital. So it's like everywhere in there, but then when you make it act like a particle, it has to be in one place. But when you're not observing it, it's occupying the whole space. So this is what that plot looks like in three-dimensional space. And so we see that there's, a lot of density here, and then as you get out here, the density decreases, and then out here, the chances of finding the electron are very, very small. Could an electron be out here? Yeah, it could. Andrew stole the big wheel and went to Kent's house, right? This sort of a plot is misleading, though, because if we look at this probability density, it's high at a distance 0 from the nucleus, and then it falls off. But this predicts that the highest chance of finding the electron is at the nucleus. But the electron is not at the nucleus. That's like the one place we know it isn't. So what do we do about that? Well, we need to look at something slightly different. Instead of looking at the distribution or the probability density, we look at what's called the radial distribution function. This is the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. And this gives us a better picture of where the electron is likely to be found. So the total radial probability is the probability divided by the unit volume, that's the probability density, times the volume of a shell at a distance r. And so as you get farther and farther from the nucleus, that becomes larger and larger. And at the nucleus, the volume of that shell is 0. And so that gives us 0 probability at the nucleus. And so this is something that works better. We've got two functions with opposite trends. So this gives us a graph like this as we're looking at total radial probability, distance from the nucleus. So the probability of it being at the nucleus is 0. As we move away, the probability increases very steeply, reaches a maximum, and then goes down as we continue out. And the probability out here is almost 0, very low. We graph that, and this predicts that the average distance of an electron from the nucleus in a hydrogen atom is 52.9 picometers. And that corresponds with the radius that Bohr predicted from his calculations. So this is reassuring. Doesn't necessarily prove anything, but it's reassuring that both of these came up with the same number. So it's the same number, the same radius, but the concept is very different. Bohr's model says the electron is always found at 52.9 picometers from the nucleus, almost like it's tethered on a string. It's going in an orbit. It's always the same distance. The quantum mechanical model said the average radius is 52.9 picometers. That's the most probable, but there's this wide range of radii that it could be. So it's not just always a fixed distance. The 2s orbitals and the 3s orbitals are also spherical in shape. They're larger in size than the 1s orbital because as you increase that principal quantum number, the energy of that level is higher and higher, and the distance from the nucleus is higher. So they're larger in size. They contain at least one node. And a node is a point where the wave function goes through zero. So this is a picture of a standing wave, like you can get going with a string. You can get a standing wave, and you can have nodes. And if you increase the frequency at which you're vibrating the string, you can change the number of nodes that are present. The probability of finding an electron at the node is 0, but then in here, it's higher. And I think the best I could possibly expect from 1A students in terms of understanding what this is, because remember, even Einstein didn't really understand this, and he didn't like it either, is that orbital is a lot like a standing wave in a string. The electron is forming a standing wave, but instead of it being this, eye-shaped or football-shaped thing, it's a sphere. And then the p and the d orbitals get even weirder. They have different shapes. So it's a three-dimensional standing wave. And if you pin down the string, if you touch it, you force it to stop. And it's not a wave anymore, it's the string. But when you're just looking at it, it looks like the string is occupying the whole space there. So I've got a video. I thought I had a link in here, but I guess I don't. This would be a good place to watch it.
It's going to come up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's go. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
So I just want to pause it there. Oh, I can't use my pointer, can I? Oh, there, I can do that. So right here, it looks like the string is occupying this whole area, right? Because it's going up and down. Oh, and pause it, there we go. There's the high-speed camera. You can see it's actually going up and down, but it looks like it's occupying the whole space.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, and the middle's a node. So we have 3 nodes for this one. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5.
So that'd be like the 1s orbital, no node.
And there we go.
The second harmonic
Basically, the
is
scenario of a
like
jump.
2s.
Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess, what is that, 25.5?
So it'd be like the 3s orbital with 2 nodes.
So that's the third harmonic. How many wavelengths is this? Well, it's 1 1/2. 1 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the 6th harmonic. The 6th harmonic will just be double this frequency. So we go up to 50. And there we go. That's the 6th harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
You guys want to do derivations? Physics? No, of course you don't. I don't either. So we're not going to do that. We'll go back to this. So this is reconnect. Seriously? So now we've seen the video with the actual string moving the standing wave. And so in the second and third levels, the s orbitals are going to have nodes, additional nodes, not just a node here at the nucleus, but then there'll be another node and another as you go up, increasing. And those are places where the electron is not found. The probability of finding the electron is 0 at the node. And yet the electron is occupying the space on both sides of the node. Well, if we think about the electron as a particle, that can't be, right? Because how can the particle go from this place to that place without going through the node where it can't be? It can't. But if we think of the electron as a wave, a standing wave describes the orbital. And the string, we saw it. It's here and it's there. And it appears to occupy the entire space on both sides of the node. And that's, I think, the best way to look at electrons. They're standing waves. Any questions? So here we can look at the radial probability distributions down here. And we see that, you know, 0 at the nucleus, and then there's this increase, and then it goes back to 0. And so you have this little bit of a standing wave here, and then you've got a 0, and then you've got more. And so there's this one node. And for the 3s orbital, there's 2 nodes. Those are the white parts here, this and this. And the 4s would have an additional node. So s orbitals, that's L equals 0. Each principal energy level only has one s orbital, because if L equals 0, there aren't any more possibilities for m sub L. M sub L has to be 0 as well. So here we have a more geometrical description of the orbital. Here it looks like a solid sphere. This is easier to draw and to think about than trying to do all the little dots like a distribution map. So it's spherical. It's really important not to think of this as a container in which the electron is found. This is just a representation of, pick a percentage, 95% chance, 70% chance that the electron will be found within this region, but it may be outside as well. When L equals 1, we call those p orbitals. Each principal energy level above n equals 1 has 3 p orbitals, because when n equals 1, then L equals 1, then m sub L can be -1, 0, and +1. So then you've got 3 different possibilities. So m sub L tells us the orientation of those orbitals. And the p orbitals have 2 lobes with a node at the nucleus. And they will also have additional nodes depending on which energy level they're in. So my iPad's lagging behind. There we go. So here's the more, time exposure description, and here's looking at it as, a solid shape. So one of the p orbitals lies along the x-axis, one lies perpendicular along the y-axis, and the other lies perpendicular to those two along the z-axis. And so this actually looks a lot more like a standing wave to me, because you can see that, it's like, okay, well, there's my standing wave, right? Kind of like that. There's a node at the nucleus, so it can't be there, and then eventually out here you're going to get to 0. And so it's not, the same sine wave shape, but it's the same idea as a standing wave on the string. The electron is simultaneously on both sides of the nucleus, which is disturbing when you think of it as a particle. But when you think of it as a wave, like, well, sure, standing wave is on both sides of the node, right? But if you try to identify where it is, then you collapse that duality into one or the other.
So you're never definitely determining where, it's more like a probability?
Yeah, you can't know where and how fast, or where and how much energy an electron has at the same time. The more you know about one, the less you know about the other. Heisenberg uncertainty principle. Mm-hmm. The d orbitals, that's when L equals 2. When L equals 2, you've got 5 possibilities from m sub L, and these are aligned differently. There are 4 different planes, and then there's a 5th one that's along the d-axis. It has a different shape. Most of these are 4-lobed, so it's kind of like a double p orbital, and then the last one is just weird looking. And again, as you go to higher principal levels, you've got more nodes in these guys. So there's the d orbitals. Aren't they lovely? These guys aren't too bad, but this one's weird. That's just weird. F orbitals. So you get to F, then L equals 3. L equals 3. And so then you've got 7 possibilities for m sub L. So you've got 7 different shapes. These don't have spherical nodes. These have planar nodes. Well, they have planar nodes, and then the higher ones have spherical nodes. So those are even weirder looking. I will not make you draw those. I couldn't draw them myself. Just know that they look like very strange balloon art, don't they? It's just weird balloon art. So the phase of an orbital, orbitals are mathematical wave functions, and a wave function can have a positive or a negative value. And it can also have nodes where the value is 0. So the sign of the wave function is called its phase, positive or negative. And when orbitals interact, they can be either in phase and interact constructively, or they can be out of phase and interact destructively. And this is going to be really important later when we talk about bonding and how these orbitals interact with each other. So here we have an s orbital, and at any given time, it only has one phase. It's either going to be positive or negative. In the p orbital, one lobe will be positive while the other's negative. Okay? So we've got all these crazy funky shapes, and yet we draw pictures of atoms as being spheres. How can they be spheres if the electrons are making all these weird shapes? Well, if you superimpose the orbitals, they're going to make a shape that is roughly spherical. And the little differences from spherical are too small for us to detect. So it appears spherical. These orbitals can superimpose three-dimensionally with each other because they are waves. They are not solid things. They are waves, and the waves can overlap with each other.